In this video, we're going to look at recapping the work that you did on differentiation last year in AS. Now, the first thing that we'll look at is the basic rule for differentiation. If you've got your function y is equal to ax to the power n, the derivative of that dy dx is going to be a times n, the power, x to the n minus 1. You take away 1 from the power. So, if I've got this function over here, y is equal to 2/3 x to the 5/4, then I can say dy dx is going to be, well, the power, 5/4 comes down to the front, so it's going to be 5/4 times by the 2/3, and then I've got x, and I've got to reduce that 5/4 by 1. I've got to take away 1 from it. So what I'm going to end up here with is 4 goes into there twice. Sorry, 2 goes into there twice, 2 goes into there once. So I'm going to be left with 5/6 x to the power 5/4, take away 1, will leave me with 1/4. And there is my derivative. The second thing that we need to look at that you would have dealt with last year was the chain rule. And that is when you've got a compound function, so when you've got something happening to x inside the bracket, and then it's being raised to power as well, then we're going to use this formula over here, or we're going to think of it in terms of the chain rule, which is when we input a second variable and we derive in terms of that variable. And that's the one that I'm going to use here. So we've got this function over here, 3 brackets 2x to the power 4 plus x, all raised to the power 3. What I'm going to start with, I'm going to start and I'm going to say let a equal 2x to the power 4 plus x. That means my statement over here is going to read y is going to equal 3a to the power 3. Now, let's just make a bit more space here. What can I do with this? I can derive this thing. I can say dy dA. Well, that's going to give me 3 times 3a to the power must be reduced by 1a squared. Over here, I've got an expression that is a is equal to 2x to the 4 plus x. So what I can do here is I can work out dA dx. So I'm going to be deriving in terms of x. So here I'm going to have 2 times 4 x to the power 3 plus 1. In other words, 8x to the power 3. So if I want to work out what dy dx is, well, it's going to be dy dA times by dA dx. And now it's simply a case of substituting what I've got there. Dy dA was this first part over here. That's going to be 9 times a. Well, a was 2x to the power 4 plus x. And that's going to be multiplied by dA dx. And what have I got for dA dx? I've got 8x cubed plus 1. And so there I have my derivative for that using the chain rule. The next thing we'll look at is this sort of a situation where you have to find the tangent to a curve. Remember, the whole point of differentiating is to find the tangent of a curve. So if I want to find the tangent, I need to find the formula for the tangent, and that I'm going to get by deriving this expression. So dy dx is going to give me 2x plus 3. Now, I want to know what the gradient is. This is, in other words, the gradient of the function at all the way along the curve. I want to know what is the gradient at x is equal to 2. At x is equal to 2, dy dx is going to be 2 times 2 plus 3, which gives me 7. And so, in other words, that's the value of my gradient. Now I just need to find the equation of the tangent. In order to do that, I use the equation for the line y minus y1 equals m brackets x minus x1. So it's going to be y minus 12 is equal to 7 brackets x minus 2. We tidy all of that up and we'll get y is going to equal 7x. That's what, minus 14 plus 12. That'll be minus 2. There is the equation of the tangent to the curve. If I want to find the equation of the normal to the curve, well, once again, I'm going to derive it to find the formula for the gradient. And we've got that as 2x plus 3. I'm still going to find out what is the gradient when x is equal to 2, because that's the point that I'm working with, and we've done that before. We've got that m is equal to 7. But now I want to get the gradient of the normal, and the normal's gradient is going to be the negative inverse of this, a reciprocal of this rather, and so that's going to be minus 1/7. And so the equation of the normal, I'm still going to use that point 212 because it's a point that lies on the line, is going to be minus 1/7 x minus 2. And now that's a little bit more messy. Y is going to be minus 1/7 x. That's going to give me plus 2/7. So that's going to be plus 12 and 2/7. Now, the next example, we have an equation that is a little bit more difficult to understand. It's not a standard parabola or something like that. Y is equal to 16 over x minus 4 root x. The normal to the curve at the point 4, 4 meets the y-axis at the point P. Find the coordinates of the point P. Now, I don't need to be too concerned about what the curve looks like. What I do need to work out is what is dy dx. Well, maybe it would help before I did that, just to rewrite this equation in a slightly easier format. This is going to be y 16x to the minus 1 minus 4x, and the square root of x I can write as being to the power of a half. So now I can work out what dy dx is. Dy dx is going to be minus 16x to the minus 2 minus 4 times a half x to the minus power of a half. So there we've got what the derivative is. They tell you the normal to the curve at the point 4 minus 4 meets the y-axis at point P. So I'm going to be dealing with this point over here. So let's find out what dy dx is at the point when x is equal to 4. So dy dx is going to be 16, 4 to the power of minus 2, minus 4 times a half, that's going to be 2. And instead of writing that x, I'm going to write 4 to the power of minus a half. Now, I know that 4 is 2 squared. So what I'm going to have here is minus 16 times by 2 to the minus 4. 2 to the minus 4 is just 1 over 16. So I'm going to get minus 16 over 16. Minus, and now I've got 2 times 2 squared to the power of a half. That's going to be 2 to the minus 1. And 2 to the minus 1 is 1 over 2. So in other words, I've got 2 over 2. I don't know why I put that equal sign there. It should be a minus sign. And so what I've got here is minus 1, which is going to give me minus 2. So that is the gradient of the curve at the point when x is equal to 4. I need a bit more space. So let's just get some more space in here. So the normal, that's going to have the gradient of this thing made negative and inverted. So this is going to have the gradient of a half. That's what the gradient of the normal is. So in other words, I'm going to have the line y minus, it was minus 4, yep, y minus 4 is equal to a half x minus 4. In other words, when I tidy all of that up, I'm going to get a half x. That's going to be a half times minus 4 is minus 2. I've got a plus 4, which I'm going to bring over. That's going to give me minus 6. So there is the equation of the normal, and it tells you that it meets the y-axis at the point P, and they want the coordinates of the point P. Well, we know this is the y-cut, and so P must have the coordinates 0 and minus 6. And so we've got an answer to that without having to draw the curve at all. Finally, the last of the examples from last year's work, finding stationary points to a curve. Well, we know that this is a cubic graph, and so the cubic graph is going to look something like that. We're looking at the stationary points. We're looking at these points over here. We know at those points that the gradient m is going to equal 0 because it's a stationary point. So what I need to first of all do is work out what the derivative is. The derivative in this case is going to be 2 times 3, that's going to be 6x squared, plus 2 times 3, that's also going to be 6, but just x this time, minus 12. And at my turning points, this thing is going to equal 0. I can take out 6, and I know that I'm going to have x squared plus x minus 2 equals 0, and that factorizes nicely to being x plus 2, x minus 1 equals 0, and so therefore I've got my x values at minus 2 or at x is equal to 1. Now, there are two ways in which we can look at this. I've got my diagram. I know that the x-axis is going to run something like that. And I know I've got one turning point at minus 2 and one turning point at 1. Obviously, this point over here must be the point at 1. This point over here must be the point where x is equal to minus 2. So that's one way in which I can figure out that this point over here must be my minimum and this point over here must be my maximum. You can, of course, go and work out the double derivative. So d2y dx squared. We go and derive this thing again, and we're going to get 12x plus 6. And then what we need to do is look at what the double derivative is when x is equal to minus 2 or when x is equal to 1. When x is equal to minus 2, d2y dx squared is going to be 12 times minus 2 plus 6. Minus 24 plus 6 is going to give me minus 18. Here my d2y dx squared, that's going to be 12 times 1 plus 6, and that's going to give me plus 18. Where my double derivative is negative, that's going to be my maximum point, and this is where my minimum point is. And that concurs with what we had up top over there. Now they want the minimum maximum values for the curve, so we know that the minimum maximum values are going to occur at these 2 points, when x is minus 2 and when x is 1. I just need to figure out what the y values are going to be. So there's the equation of the curve. At x is equal to minus 2, y is going to equal 2 times 2 cubed plus 3 times 2 squared minus 12 times 2. And that's going to come to 8, 16, 4, 12, 16, 12 is 28. Take away 24. So it's going to leave me at plus 4. at x is equal to 1, then I'm going to get y is going to equal 2 times 1 cubed plus 3 times 1 squared minus 12 times 1. That's going to give me minus 7. And so I can tell you that my maximum value is going to be at the point minus 2, 4, and my minimum is going to be at the point 1, minus 7. So hopefully that's refreshed your memory on the work that you did last year. Goodbye.